Ships are still the largest moving things made by man. While plying at sea, they face many complex and unpredictable sea waves. In the final design stage, geometrically similar models are tested in simulated sea conditions to predict ships' behavior at sea. This program introduces the towing tank at the Shipbuilding and Offshore Engineering Department of Nghi Polytechnic and demonstrates a simple model test conducted in it. First, let me tell you more about this towing tank. A towing tank is a tank for testing models, rather similar to a swimming pool. However, it is different from a swimming pool in that it is generally longer and narrower. Unlike a swimming pool, the towing tank is normally above ground level. It is usually made of concrete, but may be made of other materials also. The towing tank at the Nghi Polytechnic is a concrete tank of length 43.0 meters, breadth 4.4 meters, and depth 1.0 meter. It has a wave-generating machine on one side to generate waves by moving a paddle outward and inward horizontally. The paddle can generate waves of length between 0.38 to 9.7 meters. On the other end of the tank, there is a beach. It has a towing carriage supported by two rails 4.15 meters apart on the side walls. This carriage can tow a model at any speed between 0.25 meters per second to 2 meters per second. Moreover, it accommodates a 6-channel amplifier, a 6-pen recorder, a tachometer, a power unit, and a load cell with dynamometer. The dynamometer helps the pen recorder to draw various curves from which forces and moments acting on the model can be determined. Ship model, dynamometer, amplifier, and pen recorder are usually connected to each other like this. When the carriage moves at a certain speed, the forces and moments Fx, Fy, and Mz acting on the model are detected by the dynamometer and transferred to the pen recorder via the amplifier. Each channel of the amplifier is used for one component of forces or moments. The output from the pen recorder can later be analyzed. This type of recording can be done for different wavelengths and positions of the model, which may be analyzed to get a clear idea about forces and moments on the model. Now, let's perform a simple ship model test in this towing tank. We are interested in finding out the lateral force Fy and moment Mz at different drift angles of a model of the following particulars: length L 1.12 meters, breadth B 0.135 meters, draft D 0.0735 meters, velocity U 0.4 meters per second, lateral area A 0.0824 meters squared. The force Fy is equal to Cy times half the density of water rho times A times U squared, and similarly for the moment Mz. The coefficient Cy is equal to my times L over u times the drift angle alpha plus mx times the angular velocity omega. Cz is equal to n times L over u times the angular acceleration omega dot. Where the term mx is equal to the moment mx divided by half the density rho times A times L, and similarly for the term my. The angular velocity omega, angular acceleration omega dot, and the factor n are as given, where Iz is the moment of inertia about the z-axis. So we have the following equations for the force Fy and the moment mz. In these equations, the density rho, area A, and velocity u are known, except Cy and Cz. We can express Cy and Cz in terms of velocity u, the drift angle alpha, the angular velocity omega, and the rudder angle delta. We therefore have Cy equals to y alpha times alpha plus y omega times omega plus Fy minus y delta times delta. And similarly for the coefficient Cz. The nonlinear terms Fy and Fz can be ignored. For ships moving on a straight course, angular velocity omega must equal 0. The lift and moment coefficients y delta and n delta can be determined from a separate experiment for the rudder. After simplification, we get the following equations, where y alpha and n alpha are the static derivatives. We can find Cy and Cz by using these relations. Cy is equal to Fy divided by half the density rho times A times u squared. And similarly for the coefficient Cz. Remember, we must set the instruments before starting the experiment. But how do we do this? First, fit the ship model fitting jig onto the ship model and immerse it to the required draft by adding extra weight.
Slowly lower the cantilever. Okay, stop.
Connect the cable from the respective load cell output signal sockets to the corresponding DC strain gauge amplifiers. And from the respective DC strain gauge amplifiers to the pen recorder. Fix the load cell onto the carriage. Roughly estimate the maximum lateral force and moment from this formula. Fy is equal to y alpha times half the density rho times A times u squared. And similarly for the moment mz. Where the static derivatives y alpha and n alpha and the quantity k are as given. Let us suppose that maximum Fy is equal to 600 grams and the maximum mz is equal to 0.1923 kilogram meter. Set the DC strain gauge amplifier knob 7 at off position and the ATT knob 4 at 0. Turn the 0-point screw knob 16 at the rear panel to balance the bridge. Set ATT knob 4 to 1/20th and turn the knob 2 for coarse adjustment. Set ATT knob 4 to 1 position and turn the knob 3 for fine tuning. Add a weight of 250 grams to the load cell with ATT knob 4 setting at 1/20th. Adjust the ATT knob 5 to provide the required output from the pen recorder. 250 grams would give 20 millimeters of reading on the recorder. Similarly, for 500 grams, 40 millimeters, 750 grams, 60 millimeters, and 1000 grams, 80 millimeters. Remove the cables connected to the load cell and fit the load cell onto the towing carriage. Reconnect the cables to the load cell and fit the model ship to the load cell sensor part or dynamometer with care, keeping the x-axis in the direction of tow. This preparation is known as the calibration procedure. A set of calibrated equipment can be used repeatedly for similar types of experiments. The correct response in output depends on proper calibration. Now, we can start our experiment. Test run the carriage at about 0.4 meters per second and check whether the readings of lateral force Fy and moment mz are 0. If not, reset the angle of the ship model until Fy and mz are 0. Set the towing speed at 0.4 meters per second and carry out the experiment for roughly equal intervals of angles of drift alpha. Analyze the results of Fy and mz recorded by the pen plotter. Calculate the values of Cy and Cz using the following equations. Plot the graph of Cy and Cz against the angle of drift alpha. Slopes of these curves at the corresponding origin will give the static derivatives Y alpha and N alpha respectively. Ship model tests conducted in towing tanks play a vital role in modern ship design. With this towing tank facility, which is the only one of its kind in the region, the Department of Shipbuilding and Offshore Engineering of Nghi Polytechnic is well equipped both to train students as well as to serve the marine industry in the area of ship design.